Welcome, sleepy thinkers, curious night owls, and anyone drifting gently toward dreams. You've arrived at the DODO SCIENTISTRY, where the stars are big, the questions are bigger, and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. Did nothing ever exist? But don't worry, we'll take it slow, with soft voices and a calming curiosity. After all, this isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. Now, I do hope the video isn't too interesting. That would be terribly inconvenient at bedtime. But if it happens to keep your mind gently glowing, well, at least you'll be learning something fascinating while you drift. Before we begin our cosmic wandering, I'd love it if you tap the like button. And if you enjoy gentle science journeys like this, feel free to subscribe. It helps more curious souls find their way here. Let me know in the comments where in the world you're watching from and what time it is for you right now. Is it just past midnight? Or the early glow of 4 a.m.? I always love reading those sleepy check-ins. And finally, while we're going to explore some deep and dreamy questions tonight, please remember, this is not medical advice. Just a soft place to land at the end of your day. Let's begin. Let's take a deep breath, not to fill your lungs with cosmic insight just yet, but because we're about to dive into a subject that seems simple at first, but quickly becomes slipperier than a bar of soap in a black hole. Tonight's question is, what do we really mean by nothing? You'd think that of all the things in the universe, or outside of it, nothing would be the easiest to explain. After all, it's, well, nothing. No things. No stuff. Just emptiness, right? But here's where it gets interesting. The more carefully we examine nothing, the more it starts to look suspiciously like something. And as we'll see, in both science and philosophy, nothing can wear quite a few disguises. In fact, there are several kinds of nothing, each one stranger and more counterintuitive than the last. Let's start small, with something familiar. Picture an empty jar sitting on your kitchen counter. You screw off the lid and look inside. It appears empty. There's no peanut butter, no sugar cubes, not even a lone grain of rice. Most people would call that nothing. But of course, that's not quite right. The jar is full of air, oxygen, nitrogen, a bit of carbon dioxide, maybe even the lingering scent of cinnamon from whatever it held last week. Molecules are bouncing around in there like invisible popcorn. If you were an ant with a chemistry degree, you'd be overwhelmed by just how not nothing it really is. Okay, let's step it up a notch. What if we suck all the air out of the jar, vacuum seal it until there's no atmosphere left inside at all? Now we've got a vacuum, or what we might call empty space. Is that nothing? Well, we're getting closer. But even this vacuum isn't truly empty. First, there are still fields inside. Not cornfields, the invisible kind that exist everywhere in the universe. These are quantum fields. And according to modern physics, they can never be completely turned off. Even in their lowest energy state, they still ripple with possibility. And this is where things start to get quantum weird. In the early 20th century, scientists like Max Planck and Werner Heisenberg discovered that the tiniest levels of nature are never truly still. Even a perfect vacuum, devoid of matter and energy, is still humming with uncertainty. Tiny particles pop into and out of existence constantly. They're called virtual particles, and they're part of what physicists call quantum fluctuations. In other words, even nothing is always doing something. Imagine your empty jar again. If we could make it truly vacuum-sealed, removing every molecule of air, and then shrink ourselves down to the quantum scale, we'd still see things happening, not because matter is leaking in, but because the fabric of the universe itself is restless. It fizzes with energy. The vacuum is like a quiet ocean that looks calm from above, but teems with life below the surface. So here we are, two versions of nothing down, and neither one is truly empty. Let's take it further. What if we removed space itself? Not just the stuff in space, but space itself, gone. No dimensions. No up or down. No left. No right. Can we even imagine that? This is where language starts to fail us. Without space, we can't describe where anything is or even where nothing could be. It's not a black void. It's not a white screen. It's not darkness, silence, or emptiness. It's the absence of place itself. You can't put your mind inside it because there's no inside. Then let's get even more radical. What if we took away time as well? No seconds ticking by. No change. No motion. A timeless, spaceless, matterless what? Some physicists and philosophers propose that this is the only true form of nothing, the absolute absence of everything, including the dimensions in which things can exist or happen. But now we're dealing with something almost paradoxical. If there's no space or time, can we even say it exists? And if it doesn't exist, then what is it? It's a bit like trying to draw a square circle. The words make sense individually, but together they become nonsense. In the same way, our brains, which evolved to track fruit, faces, and predator footprints, aren't naturally equipped to visualize the absence of all things. Nothing, in its most extreme definition, might be not just beyond our senses, but beyond thought itself. Of course, some philosophers have argued that nothing doesn't make sense at all, that it's a concept invented by language. When we say something is not there, like when your friend says, "There's nothing in the fridge," we still mean something. We mean the fridge is present, just empty of the items we want. But when we talk about absolute nothingness, we're using words that point to an absence we've never encountered. Heidegger, the famously cryptic German philosopher, once asked, "Why is there something rather than nothing?" It's one of those questions that sounds obvious at first, but grows more unsettling the longer you think about it. And the more we learn from science, the more it seems that nothing might not just be hard to find, it might not exist at all. Even the term before the Big Bang may already be a kind of error. If time began with the universe, then asking what came before is like asking what's north of the North Pole. The question seems to make sense, but collapses under its own logic. Still, it's a very human question. We crave origin stories. We like to trace things back. Family trees. Historical timelines. The last slice of cake. But when it comes to the universe, we may hit a wall. A soft, baffling, quantum fluctuating wall. So, where does that leave us? It leaves us with several kinds of nothing, all of which are actually quite something. From airless jars to seething quantum vacuums to theoretical voids outside of space and time, nothing is not one neat concept. It's a spectrum of increasingly abstract possibilities. And in the end, we might have to accept that pure, total nothingness may not be part of reality at all, only part of our imagination. But that doesn't mean the question is pointless. Quite the opposite. Asking what nothing is helps us understand what something really means. It's in the contrast that clarity emerges, or at least a kind of peaceful confusion. And as we'll see when we explore the origin of the universe, nothing may be not the end of the line, but the beginning of a very strange road. So, let's keep floating gently through the questions. There's a lot of nothing left to uncover. Let's take a gentle step forward, or maybe backward, depending on how you think about time. We're going to take a calm stroll through the history of, well, everything. But don't worry, you won't need a time machine or a seatbelt. Just a quiet mind, a comfortable pillow, and perhaps a sense of cosmic wonder. Tonight, we're visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang. Not a loud explosion in space, despite the dramatic name, but a gentle unraveling of space itself. A moment so strange that it gave birth to not only everything we see, but the very space and time in which we see it. Let's imagine you're standing in the deepest corner of space, far from any stars or galaxies. There's no sound, no breeze, just the soft hum of distant starlight and the feeling of cosmic stillness. That stillness, though, hides a secret, because everything, all the planets, stars, galaxies, and even the emptiness between them, is moving apart. Slowly, gently, and inevitably space itself is stretching. This idea, that the universe is expanding, was one of the great revelations of the 20th century. For a long time, scientists assumed the cosmos was static, fixed, eternal, unchanging. But then, in the 1920s, a Belgian priest and physicist named Georges Lemaitre had a very curious idea. What if the universe was not static, but expanding outward from a single dense point? Around the same time, American astronomer Edwin Hubble was peering through his telescope and making an equally curious observation. The light from distant galaxies wasn't just dim, it was redder than expected. Not because they were embarrassed, but because they were moving away from us. This shift in wavelength, known as redshift, was a cosmic clue. It meant space was stretching, and everything in it was being carried along, like raisins in a rising loaf of bread. And if everything is moving apart, then it must have once been much closer together. Imagine rewinding the universe like a film played in reverse. Galaxies rushing toward each other, stars condensing, matter folding inward, all collapsing into a tighter and tighter ball, until, about 13.8 billion years ago, you reach a moment of unimaginable density and temperature. A kind of cosmic seed, a singularity, as it's sometimes called. Not a thing inside space, but the point at which space itself began. This is what we call the Big Bang. It wasn't an explosion in space. There was no pre-existing vacuum, no cosmic firework lighting up a black sky. Instead, it was the sudden, dramatic expansion of space itself, the birth of time, energy, and the laws of physics as we know them. And no matter where you stand in the universe, it looks like everything is expanding away from you. Not because you're special, but because space itself is growing in all directions. It's a bit like dots drawn on the surface of a balloon. As the balloon inflates, each dot moves away from the others. Not because they're traveling across the surface, but because the surface itself is expanding. That's our universe. A balloon of SpaceTime, slowly inflating for billions of years. Comment what happened in the first moments. Now, what actually happened in the first moments of this expansion? That's where things get delightfully complex. In the tiniest fractions of a second after the Big Bang, and we're talking trillionths of a trillionth of a second, the universe was a hot, dense plasma of particles and energy. Temperatures were so high that matter couldn't exist in the forms we recognize. Protons and neutrons hadn't formed yet. Even atoms were still a future luxury. Everything was a glowing soup of fundamental ingredients. But as the universe expanded, it also cooled. That cooling allowed energy to condense into particles. Quarks began to combine into protons and neutrons. After a few minutes, these joined to form the first simple nuclei, mostly hydrogen and a little helium. Fast forward a few 100,000 years, a blink by cosmic standards. And the universe had cooled enough for electrons to settle into orbits around nuclei. For the first time, neutral atoms formed, and something beautiful happened. Light, which had been bouncing off free particles like a strobe in a foggy room, could finally travel freely. This moment, when the universe became transparent, left behind a whisper, a kind of soft ancient glow still visible today. It's called the cosmic microwave background, or CMB for short, and it's one of the strongest pieces of evidence we have for the Big Bang. The CMB is everywhere. It fills the universe with a faint, nearly uniform microwave signal. It's not strong. You'd need a very sensitive antenna to detect it. But it's there like a baby picture of the cosmos frozen in time. Tiny temperature fluctuations in this ancient light give us clues about the earlier structures. The seeds of galaxies, stars, and planets. Discovered in the 1960s, almost by accident, by two radio astronomers, Arno Penzias and Robert Wilson. The CMB was a game changer. They thought the static they were hearing was from pigeon droppings on their antenna. It turned out to be the echo of creation. Similarly, the universe may have been unpowered, so to speak, until the Big Bang flipped the switch. And with that flip came time, space, energy, and all the cosmic ingredients that followed. Of course, this raises a different kind of question. If time began at the Big Bang, what caused the Big Bang? Doesn't a cause require time to precede effect? You're not alone in asking that. It's one of the slipperiest concepts in all of physics. Most cause and effect relationships we know depend on time flowing forward. You toss a ball, then it flies. You pour tea, then it fills the cup. But if the universe began in a timeless state, the normal rules don't seem to apply. Some physicists speculate that the cause of the Big Bang may not be a cause in time, but a kind of boundary condition, a set of starting rules that simply are like a board game that springs into being with the dice already in motion. There is no first player, because the rules themselves begin the game. And here's another twist. Not all physicists even agree that time had a sharp beginning. Some models suggest that time may be more like a loop or a bounce, contracting and expanding in cycles, with no true beginning or end. We'll visit those ideas later on when we explore theories like the Big Bounce and loop quantum cosmology. But for now, let's stay with this strange but simple notion that time had a beginning, that it emerged from the Big Bang, just like light, matter, and motion. That before the universe, there wasn't a clock ticking in a dark room, waiting for someone to press start. It's hard to wrap our heads around because our heads evolved to keep track of days and seasons, not the curvature of space-time. But in some ways, it's a liberating idea. If time had a birthday, then every second that exists, including this one right now, is part of a grand unfolding. A story that began 13.8 billion years ago, and is still being written. And perhaps most remarkably, every moment we experience is layered within that cosmic timeline. The ticking of your heartbeat, the flicker of neurons in your brain, the soft rustle of your bedsheets, all of it part of time's fabric. A fabric that, according to our best understanding, didn't always exist. The next time someone casually asks you, what happened before the Big Bang? You can smile sleepily and say, that's like asking what's north of the North Pole. Then you can sip your tea and drift into the kind of dream only the universe itself could imagine, because time, like a river, had a source. And for reasons we may never fully grasp, that source seems to have emerged not within time, but alongside it. Time had a beginning, and here we are, floating in its current. Quantum field theory tells us that everything, every particle, every force is a ripple in a field. Imagine the universe as a vast ocean, but not of water. Instead, this ocean is made up of fields, invisible layers of energy that stretch across all of space. There's a field for electrons, a field for quarks, a field for photons, even a field for the Higgs boson. These fields aren't confined to specific locations. They exist everywhere all the time. Now, here's the magical part. When a field vibrates in just the right way, it produces what we see as a particle. An electron is just a ripple in the electron field. A photon, a ripple in the electromagnetic field. It's like throwing a stone into a pond and watching the waves spread out. Only in this case, the ripple is the stone. But even when the pond seems perfectly still, no ripples, no wind, there's still energy. At the quantum level, fields are never truly at rest. They wiggle spontaneously due to the strange rules of uncertainty that govern the quantum world. This is where quantum fluctuations come in. According to the Heisenberg uncertainty principle, there's a limit to how precisely we can know both the energy and the timing of events. This means that even in a vacuum where there are no particles and no radiation, energy can temporarily spike. For the briefest moments, particles can flicker into existence and then disappear again. These are called virtual particles. And while they're not directly observable in the way normal particles are, their effects can be measured. It's a bit like borrowing a cup of sugar from your neighbor and returning it so fast they don't even notice you were there. Except you're a pair of subatomic particles, and your neighbor is the universe. So when we say the vacuum isn't empty, we don't mean it's secretly full of stuff. We mean that even in its lowest energy state, space is still humming with jittery, temporary excitations. These fluctuations are incredibly brief and small, but they are real enough to have measurable consequences. For instance, quantum fluctuations can shift the energy levels of electrons in atoms, a phenomenon known as the Lamb shift. They can cause forces to emerge between uncharged metal plates placed very close together in what's known as the Casimir effect. And they may even be responsible for some of the randomness that underlies radioactive decay. But here's where things get really fascinating and relevant to our larger question. Could this fluctuating jittery vacuum be the true origin of our universe? Some physicists think it might be. Let's drift into the idea slowly. If space can never be truly empty, and if quantum fluctuations are always bubbling beneath the surface, then maybe, just maybe, a fluctuation of the right kind could cause something big to happen. Something like the birth of a universe. One proposal suggested by physicist Alexander Valenin is that the universe could have tunneled into existence from nothing. Not nothing in the philosophical sense, but a kind of quantum nothing, a state with no classical space or time, but with the potential to fluctuate due to quantum uncertainty. In this view, the universe wasn't caused by anything in the traditional sense. It didn't explode out of a pre-existing space or emerge from a deity's command. Instead, it could have spontaneously appeared, a quantum fluctuation on a cosmic scale, allowed by the rules of quantum mechanics. To be clear, this isn't magic. It's not a loophole. In the quantum world, spontaneous events with non-zero probability can and do happen. It's just that most of them are tiny and fleeting. But if the conditions are right, if the vacuum has enough energy, for example, a fluctuation could trigger inflation, the rapid expansion that set the stage for the Big Bang as we know it. In this sense, the universe may have emerged from a vacuum state, not in absolute nothing, but a seething dynamic field of potential. The kind of nothing that's actually quite something. Now, some of you might be thinking, wait, doesn't this still leave us with something? Where did the quantum fields come from in the first place? And that's a fair question. This approach may push the mystery back a level, but it doesn't erase it. If quantum fields are eternal, then we're no longer asking where the universe came from, but why these fields exist at all. If they're not eternal, then we're back to wondering what gave rise to them. But the beauty of this idea, this quantum vacuum, is that it shows us a possible bridge between nothing and something. It blurs the boundary. It hints that what we used to think of as nothing, a silent void, may be the very stage on which existence performs its quietest, strangest magic. And it makes sense in a way that the universe would be born not from a bang, but from a ripple, a flutter in the stillness, a whisper in the dark. So as you lie there letting your thoughts drift like particles in a warm breeze, remember that even the quietest, emptiest places are not truly empty, not at the quantum level. They vibrate, they shimmer, they dream. And if our universe did emerge from one of those dreams, if this vast cosmos was born from a brief, improbable flicker, then perhaps nothingness isn't the end of thought, but the beginning. The vacuum isn't empty. It's just full of potential. Let's imagine just for a moment the quietest silence possible. A silence not just without sound, but without time. Not just without motion, but without space. No stars, no atoms, no energy, no past, no future. Not even a black void. Just the absence of everything. And then, a universe. This might sound like the setup for a bedtime fairy tale. Once upon a time, there was no time. But in the curious world of theoretical physics, it's more than a bedtime story. It's a serious attempt to understand how everything could have emerged from what we once called nothing. Tonight, we're going to float gently into one of the boldest ideas in modern cosmology, the notion that the universe could have quantum tunneled into existence. A model proposed by physicist Alexander Valenin and others where reality itself flickered into being not from a divine command or a fiery explosion, but from a quiet quantum possibility. Now, before we tiptoe into tunneling, let's revisit something we learned in the last chapter. The vacuum is never truly empty. Even the calmer space bubbles with quantum fluctuations, little borrowings of energy that vanish as quickly as they appear. This is because of the strange logic of the quantum world, where things that are forbidden in classical physics can still happen as long as they don't last too long. And this idea that nature has some flexibility, a kind of quantum wiggle room, brings us to quantum tunneling. In classical physics, if you throw a ball at a wall, and it doesn't have enough energy to get over the top. It will just bounce back. That's it. Game over. But in quantum physics, there's a chance, a small but real one, that the ball could simply appear on the other side of the wall. Not because it jumped over or tunneled through in the usual sense, but because particles aren't like tiny marbles. They're like waves, fuzzy, probabilistic, slightly mischievous. Waves. And sometimes those waves allow things to appear where they shouldn't be allowed according to our everyday expectations. This phenomenon, known as quantum tunneling, is not just theory. It's been observed in countless experiments. It's how nuclear fusion happens in stars. It's how some particles decay. And it might just be how the universe was born. So, how does that work? Let's ease into Alexander Valinin's idea, one of the most quietly radical ideas in all of cosmology. In the early 1980s, Valinin proposed that the universe could have tunneled into existence from a state with no classical space, no time, and no matter. In other words, from nothing. But this wasn't an ordinary nothing. It wasn't empty space. It wasn't a vacuum waiting to be filled. It was the absence of all physical structure, yet somehow still governed by the rules of quantum physics. This sounds strange, and it is. But remember, quantum physics allows for possibilities that defy classical intuition. In Valinin's model, the universe didn't need a cause in the traditional sense. There was no ticking clock before it, no spatial coordinates to mark its arrival. Instead, it was like a particle appearing on the other side of an impossibly high wall. Not because it climbed over, but because the laws of quantum mechanics gave it a tiny but non-zero chance to exist there. This is sometimes called quantum cosmogenesis, the birth of a cosmos through quantum means, and it comes with a remarkable feature. The probability of tunneling is related to the energy of the resulting universe. That is, smaller, simpler universes more likely to tunnel into existence than larger or more complicated ones. Now, if you're wondering, wait, how can quantum laws exist in a place with no space or time? You're not alone. It's a delicate philosophical and scientific question. Some physicists argue that quantum laws are so fundamental they don't need a pre-existing universe to operate. They're not like traffic rules written on signs. They're more like the blueprint of possibility itself. You can think of it like this. Even if there is no game board yet, the rules of chess still exist conceptually. And once the board appears, those rules dictate how pieces can move. Similarly, the pre-universe, nothing in Valinin's model doesn't have a game board, no spacing, no geometry, but it may still be shaped by quantum rules that determine what can happen and how likely it is to happen. And according to this idea, what can happen is astonishing. An entire universe complete with its own space, time, energy, and physical laws can tunnel into being, and we might be living in it. So, where does this leave us in our journey to understand nothing? Well, it shifts the question a bit. In Valinin's model, there may be no before the universe in the traditional sense, but there is a mathematical space of possibility, described by quantum laws. The nothingness isn't an empty box. It's more like a potential, a kind of seedbed, of realities that could bloom given the right moment, or perhaps more accurately, given the right absence of moment, since time itself doesn't yet exist in this state. This idea of the universe as a spontaneous probabilistic event might feel strange, or even a little unsatisfying. We're used to thinking of causes. Things happen because of something else. But in the quantum world, some events don't need causes in the usual sense. They're allowed to happen by the rules of probability, not by the rules of determinism. And what's especially lovely about Valinin's model is that it doesn't require any exotic ingredients, no mysterious pre-existing space, no divine spark, just quantum mechanics doing what it always does, allowing unlikely things to happen given enough time, or in this case, giving birth to time itself. Of course, this is still speculative. No one has a telescope powerful enough to peer before the Big Bang, or into the quantum fuzz that may have preceded it. These are ideas grounded in mathematics and theory, not direct observation, but they offer a tantalizing glimpse at how the universe might have emerged not in a bang, but in a whisper of possibility becoming reality. It was more poetic, more meditative. He urged us not to explain nothing away, but to experience its strangeness. The void, he said, reveals the fragility of existence, that it's not a given and could have been otherwise or not at all. That's perhaps the most profound insight. Nothing isn't just emptiness. It's a pause, a space for reflection, a mystery, not a flaw. And the fact that we don't know doesn't make us small. It makes us part of something greater. Maybe the universe tunneled from a vacuum, bounced from a previous cosmos, or emerged from nothing. Whatever the case, here we are, alive, aware, and able to ask. And that alone is a miracle. A ripple in space-time, asking what stirred the water. So, as you drift into sleep, let the questions glow like quiet lanterns. Because the beauty of the universe isn't only in what we know, but also in what we don't. Some mysteries aren't for solving. They're for savoring. Perhaps nothing is the mother of all things. Perhaps it was never real at all. Either way, it's okay not to know. Not knowing isn't a weakness. It's the beginning. It's a mathematical trick, used to describe quantum systems more easily. Instead of time ticking along a straight line like a train schedule, it curves into a circular Euclidean geometry. By rotating time into this imaginary dimension, Hawking and Hartle were able to model a universe that is smooth, self-contained, and singularity-free. A universe that simply is, with no sharp beginning to explain away. So, what does this mean for nothing? Well, in this picture, there is no before the universe. Because time itself doesn't extend past that smooth origin. The question, what came before the Big Bang, becomes as meaningless as what's south of the South Pole? This doesn't mean the universe popped out of nothing like a rabbit from a hat. The universe may not have begun with a bang, but with a gentle curve, no edge, no before, just a timeless unfolding of space and time. The no-boundary proposal imagines a cosmos with no singular start, self-contained and smoothly arising like the surface of a globe. While unproven, it offers a profound shift. Beginnings aren't jolts, but soft transitions. Philosophically, it invites us to embrace nothingness, not as emptiness, but as mystery, a pause, a possibility, a sacred space for awe. We may never know where it all came from, a quantum vacuum, a past universe, or nothing at all. But we're here, conscious, curious, and capable of asking. And maybe that's enough. To be a ripple in space-time, wondering what stirred the waters. Some truths aren't for solving, but for savoring. The line between nothing and something? Maybe it's not a line, but a dance. And not knowing is the beginning of wonder. Let me know if you want a version under 100. Not knowing is not a weakness. It's an opening, a beginning, a softly lit doorway to awe. So here, at the end of this journey, through nothing, we return to where we started. Did nothing ever exist? Could there have been a time before time? A place before space? A moment before everything? We still don't know. And that's what makes it so incredibly beautiful.